maybe a little less high in this case. So that shows, just like this, that it's very important to determine for different material properties this Q star, because it really depends on the materials. So in the gravitational phase, then you have to compute the fragments after the fragment evolution, after this damage has been done. And for this, we have a n-body code which allows, when the fragments evolve, not only to compute their gravitational interaction, but also to detect collision between them and possibly make them merge together, reaccumulate together. So for this, we have different criteria. I will not go into details for now, but that allowed already to well, first to make the cover of Science, but also to reproduce the asteroid families in the main belts, which are groups of small bodies that share the same orbital and spectral properties between Mars and Jupiter, and that we believed came from the same parent body which was disrupted. And our simulations were the first to reproduce these families. And what we found is that when you break a body of a few tens of kilometers, or even a few kilometers in size, first you pulverize it. But then, even if you pulverize it in very teeny fragments of a few meters in size, these fragments are massive enough to interact and eventually, sometimes, reaccumulate and form larger bodies. And at the end, the size distribution that you get is mainly composed of fragments reaccumulated down to the resolution limit. So this reaccumulation process is very effective. And I'm going to show you a few movies showing that. So for instance, here we disrupted a 100-kilometer asteroids. Most of the fragments here are about a few meters in size. So if the process was complete here, I would say, okay, the fragments for this impact energy are a few meters in size. But that's not correct, because actually after the gravity takes place, gravitational evolution takes place, you see that at the end, the largest fragment which will be larger than what was produced by fragmentation, simply due to reaccumulation. So you see it's kind of effective. Another one which shows you the same thing. Reaccumulation takes place very rapidly in this case. So it shows that you really need to account for gravity as long as the fragments are larger than a few hundred meters in size. That was the conclusion of this paper, where we found that most of the fragments which are larger than 100 meters are formed by reaccumulation. And we also showed later that the impact energy highly depends, to achieve a certain degree of disruption, highly depends on the internal structure. And also the outcome itself depends on the internal structure. So then we improved, because not only we want to know the size distribution, but also if we can have information on the shape of the reaccumulated fragments and the rotation. It's also important, because of course rotation is also something which we need to know when we want to make a deflection. And for this, as you saw in the movie, when we reaccumulated in our first simulations, we simply replaced the fragments by a sphere which contains the sum of the mass of the reaccumulated bodies. So we could not reproduce the shapes, and study the shapes and rotation. So we made an improvement of the numerical code, and now particles can stick on contact. They can form really aggregates which grow, liberate particles when they collide with a higher velocity than the mutual escape velocity, etc. I will come a little later in details if you want about this, but this is very heavy computation then, because you don't replace all fragments by one, you already with all the fragments. We also give to these aggregates which form some strengths, etc. So just to show you an example here, so these are the same movies as what I showed, but then you're going to see really aggregates forming, and that will be represented by the colors. So here it's a 25-kilometer size fragment. You see the aggregates forming, reaccumulating even. This is centered to the largest fragment, which will contain about 50% of the mass. Actually, this is close to Q star. You see here this one coming in again, exploding and liberating particles. Of course, there are many free parameters, but then still you can study the shape depending on the free parameters. And for this one, it's very nice, because we reproduce exactly the size of the shape of Itokawa, which was observed by the mission Hayabusa, and which actually was thought to be formed by this kind of scenario. So of course, don't take it as a pure match, it's just a luck. But it shows that reaccumulation is very effective, and you can reaccumulate a lot of boulders even much later after the fragmentation phase. This takes in real time about a few days to take place, or sometimes a few hours, depending on the impact energy. A few months of computer time. So now let's come to the. So after that, we looked for different impact conditions which allows to get 50% of the mass of the target in the largest fragment for different target radius. And these are the outcomes that we find for non-porous and porous body. So our study allows really to get a law which tells you, okay, I have this body, I have these material properties, what is the impact energy that I should avoid to put to my projectile in order to just make a deflection and not disrupt it. And this is for an impact velocity of 3 km per second. Then, of course, we have it for different velocities. We made it also for 5 km per second. The thing which is interesting is that actually, and that's kind of good finally, is that porous or non-porous is not drastically different. So that's already something positive. So you don't really need, if you just are interested in order of magnitude, you don't really need to have a detailed information of the internal structure. This is something which is a good thing for the study. So these are for higher velocity, so we can also scale this Q star with velocity. And of course, the higher the velocity of the projectile, the higher is the impact energy that you need to make a disruption. And this also for pumice and basalt materials. I have a movie, but I don't have that to show you. And also, not only we look at the Q star value, but also at the size distribution of the fragments. And as you can see, this is a scale for different diameter of the target. And actually, what we find is that basically it's independent of the target size. So that's also a good thing. You can characterize the Q star. Once you have Q star, you have also the size distribution, which is about common for different target size, as long as you are in the gravity regime. And also, let's see, and for different impact speed also, basically you get about the same impact velocity. These are curve for different impact velocity for 3 km per second to 10. I took a target of 300 meters because this is the most relevant for a deflection, like for apophyse, for instance. This would be the case. We also can fit with Power law, so we can give simple rules in order to characterize the outcome of a collision at these impact energy thresholds. So here is, for instance, for a 300 meter. No, this is for a 300 meter non-porous target, and this is for a porous target. You can derive a slope for the size distribution. Here, the projectile that you need is 10 meters. Here is about 9.3 meters. So you see, it's not drastically different. The projectile that you need. And you can also get the information on the ejection velocities of the fragments, which are also important for the dynamics of a spacecraft you would like to measure the deflection. And you can see that it scales the ejection velocity of the largest fragment, the median velocity, and the mean velocity, scale quite well with the radius of the target that you are looking at. This is for non-porous and this is for porous. Yeah, and then you can also get information of the diameter of the fragment as a function of the ejection velocities. So just to say that we can provide all these informations, which are impact energy threshold for disruption for targets of different sizes, from centimeter to hundreds of kilometers, of different kinds. Here we could only concentrate for 4 months on non-porous and porous bodies represented by basalt and pumice. And then for a range of impact velocities. And we also provide with that the resulting size and speed distribution for fragments and some scaling rules for an easy implementation in numerical models. And finally, the properties are, of course, to characterize this Q star for different other materials, looking for all the parameters that can be varied. Particularly, it would be nice to see also for ice or ginseng, or also for rubble pies or differentiated bodies or other shapes. Here we only took a spherical shape. And other things that we can discuss later. Thank you.